Yeah, so the recording has started. So you can always hit the present now button and start.
So can you see it?
Yeah, we can. We can. I guess everybody can, right?
So I'm going to talk about applications of group theory in
Okay, just
molecular
one thing,
vibration.
Shubhadeep. I'm not the only one in the audience. Okay, so you don't have to address me. Just speak freely to everybody.
Okay, sir.
Okay, go ahead.
So in this here I am going to talk about applications of group theory in molecular vibrations. So basically, here is the outline of my talk. I have mm, done this presentation from two perspectives, from classical and quantum mechanical treatment. First, I will go with the classical treatment, and the main advantage will come in the quantum mechanical treatment. So here, when we classically deal with this any molecular system, there is a classical Lagrangian for the system. This Lagrangian is made on the assumption that the molecular bonds are basically some kind of strings which follow Hooke's law. That is, their potentials are proportional to the, I mean, highest depend on the highest power, which is 2. So this is the most general Lagrangian that a molecule can follow from the approximation that we are following. Now, if we use this Lagrangian to solve a problem, the kind of problem that we are mostly interested in is finding the normal modes, because any vibration can be decomposed into a linear combination of the normal modes. So the problem is, if we write down the equation of motion from this Lagrangian and try to solve it, we will end up by getting a 3n times n matrix. I think I missed a cross here. This will be 3n cross n matrix. I mean 3n cross 3n matrix. We will have to diagonalize such a matrix to get all the frequencies, and the eigen vectors will be the normal modes. Thing is, getting the normal modes in this way is very tedious. I mean, sometimes, for example, for 4 atoms, we'll have to diagonalize a 16 cross 16 molecule, even though the most of the vibration are confined in a plane. So,
16 by 16, you said.
sorry, but 12 by 12.
Okay.
So our goal will be to extract some informations that we can extract even without diagonalizing such a big matrix. For example, suppose we are just interested in the eigenvectors and not the eigenvalues. That is, we are not interested in the exact frequencies. We are just interested in how the normal modes look. Well, that kind of problem, or maybe with some approximated range of frequencies, this kind of problem we can address from the perspective of group theory. So this is what we will discuss. So as an example, I have taken a simple molecule, the water molecule. It has some first of all, before studying any molecule from the perspective of group theory, we have to look at the symmetries of the molecule. By symmetry, I mean some operations which we apply on the physical space, that is R3, that after applying such an operation, the molecule should remain. I mean, the configuration should remain same. That is, the changed configuration should be indistinguishable from the configuration it was before applying the operation. So, for example, here the water molecule, we can rotate the water molecule through an axis which passes through the oxygen atom. Here the oxygen atoms are denoted by red color. The first this operation is a rotation about this axis. This is a 180-degree rotation. This is clearly a symmetry of the molecule. Here what we are doing is a reflection about this plane, and here we are doing a reflection about a different plane. So there are different names for these particular operations. For example, this is denoted as C2. Now there are many different naming conventions. As I have used this naming convention, I just want to say a little bit about this particular naming. Usually, Cn is used to express any rotation by 360-degree by n angle about an axis, and sigma v is a reflection about a plane which contains the axis, and sigma v prime is another plane. This sigma subscript v is a notation for a and v for vertical, which means that the plane is passing through this axis. Now, for molecules which have more than one axis, in that case, we consider a convention that we define something called the principal axis, where the axis around which we get maximum number of rotations, we call that axis the principal axis. And with respect to that, we name the other planes like this sigma v or other things. So here, actually, it can be shown that the only symmetries of a molecule are these symmetries. No other symmetries are possible. So this is an exhaustive list of the symmetries. And this group is called C2V. This is the name of the group. Now, to analyze any group, I mean, to analyze any molecule and its vibrations, what we need to do is we first have to look at the character table of the molecule. By character table, because character table captures all the information a group can, in most of the information a group can have. So here the actually C2V is actually isomorphic to the group Z2 cross Z2. So this is an abelian group, so we get all the equivalence classes as one dimensional. And all the equivalence classes contain exactly one element, and the constructing the character table is a trivial task, because we just um, uh, n- there is one identity a trivial representation, and the other representation we get by choosing any two of the group operations and put -1 for them. Now, here also I've used some naming conventions, some conventional naming conventions are used. That is, uh, A is denoted to A and B. These are nomenclature for one-dimensional representations. And A is used when the character of the principal axis is 1, and B is used when character of the principal axis is -1. As we have two representations for which the character of the principal axis is 1, we have used these subscripts 1 and 2. Now, this column I will come later because this will be useful later. So I'm just keeping this part. I will come to this part later. So first of all, our goal will be that this oxygen atom we have, to get the normal modes, first we have to build a representation of this group on the physical space. we have considered we have already assumed that the molecular vibrations will be confined in a two dimension. We have made this assumption because we mm, the calculation will be much simpler there because we have only r to the power 6 as the representation space. So what we are doing is here we have chosen six bases. These bases are defined like this, and have ordered these bases as Z1, X1, Z2, X2, Z3, X3. With this ordering, we can represent each of the group elements, their representations as 6 by 6 matrices, and they will look like this. C2 and CV sigma V will be equal, and the identity operation and sigma V prime will be equal. Now, usually these representations are reducible. Here also this will be reducible. Our goal will be to construct the irreducible representations because they will give us clue for the normal modes. The way we will do it is we will calculate the character of these representations. There is this representation that we have just found, we will call it chi. The characters are like this. Then we will decompose this character as a linear, as a sum of the irreducible representations. We have decomposed the representation as sum of these representations, and we are seeing that there are six one-dimensional representations. The representation that we are considering is
Shubhadev, if what you have written is right, then it cannot be 3a1 plus 3b1, right? Because as I can see, 3a1 plus 3b1 would have given you a character of 6060. So either your sigma v prime is mixed up. I guess that's more likely, right? Because
yeah.
you just added 3a1 plus 3b1. You can immediately see that, right? It's something
Yeah,
that you
yeah.
worked out in your head.
This actually will be reversed. This will be sigma v prime, and this will be sigma v.
Are you sure about the entire table, or is this just the last line that's mixed up? That is
This
6006 or 6060?
this will be 6060. Then
Yeah, because if you were to just interchange the two columns, the thing will still be wrong, right? You can't
yeah,
interchange the two
I
columns
mean
in
we
all.
will yeah, these two blocks will just get changed.
Yeah, right. Okay, fine. Go ahead.
Uh, Now, from the character table, we can actually see. Okay, now I have to go back and say something about this particular column. What we are doing is we are seeing that here there is x, y, and z. Now these are actually we have already we can already construct the representations of these uh, elements in R3. That is, if we have just I cap, j cap, k cap, these three basis vectors, we can construct the represent 3 into 3 representation of these operators because we know how they act on them. From that, we can construct the function space representations where the functions are defined on R3. And in those function space representations, we can construct basis functions. And these are just the basis functions, the z, x, and y. For instance, if we see this z function, that is this is a function which take x, y, and z and gives out the z, then we'll see that these elements will act on Z and give these eigenvalues. These are just one dimensional representations. For x and y also, when C2 will act on x, it will give minus x. In this way, this is constructed, and these actually give us a clue how uh, translations and how translations are involved. I mean, how translations are affected by these group operations. The thing is, when we are looking at the normal modes, vibrations, there are uh, uh, some transformations which are not vibrations, because in vibrations the relative motions of the molecules get changed. But suppose all the atoms are going upward in the Z direction, then that will not be a vibration, that will be a translational motion. Now, the reason we are more interested in vibrational motion, because in spectroscopy we are interested in vibrational spectra, because all the vibrational spectra lie in a certain range of frequencies in the IR regime. But translational modes, they can absorb much higher values of frequencies. So, if we want to characterize some IR spectrum, then we will be interested in vibrational modes. So, for that reason, we will take out the translation and rotation part from it, and will concentrate on the vibrational mode. Rotation, because rotations usually lie in the microwave regime, so that is very small. The IR regime is a little bit larger. So, uh, so translations, we can see that in two dimension there can be two translations, x and y. So both these sorry, the way I have drawn it, the translation will remain in x and z plane. So we will concentrate on these two representations, A1 and B1. They give some translational components. So we have to subtract A1 and B1 from these. And if we have to subtract one extra B1 from this because of the rotation Ry. And how this rotation Ry is related to this By representation? Because if we think about the Ry rotation, if we apply a B1, then exactly these eigenvalues come out. That is, if we, uh, for example, imagine this. This is our sigma v plane. So my then this little bit difficult to say. This will happen if we just there is another way of actually looking at is, that is rotations basically transform as for example ry transform as uh, z times let's say there is another vector p which transform like these components which we call p, then ry will for example rz will transform like xpy minus ypx, just like the angular momentum thing. So this way these rotations are associated with these irreducible representations, and we will subtract these rotation which appear here, b1, and two translation from this, because the rotation about y-axis is the rotation on this plane. If the whole molecule rotates by some axis, that doesn't give any vibrational mode. So the for more representations that will be responsible only for the vibrational modes will be this 2a1 direct sum b1. Now we can also construct the eigen vectors which correspond to the normal modes by looking at the projection operators. I made a small mistake here. This will be capital D because these are not the characters, these are representations. What I wanted to do is construct the matrix which will project onto the irreducible subspace of A1. So this will be a 6 into 6 matrix. I think I've written this. Yes. So this projection operator includes a translation, because here we can see this along the Z there is a translation, and other vibrational modes. So if we subtract translation from this projection operator, if we subtract the projection operator corresponding to translation, then we will remain with only the vibrational modes. So for that we have constructed the translation projection onto the translation mode. The projection actually is this cat psi bra psi kind of thing, where this vector is one in z1, one in z2, and one in z3, because all of them are moving in the z direction. So if we construct this projection operator and subtract it from the A1 projection operator, what we have is a projection operator will be project only on the vibrational modes. So if we see the eigenvectors of this matrix, we will see the vibrational modes, and the eigenvectors come out to be these two. Both have eigenvalue 1, as a projection operator should have. There are other four-dimensional eigenspace which has zero eigenvalue. So uh, these actually correspond to two vibrational mode, which we'll call the stretching mode and bending mode. Now these individually they are not associated with stretching mode and bending mode. One of their linear combination is stretching mode, and one of their linear combination is the bending mode. Well, stretching mode actually looks like if these two hydrogen atom are uh, uh, moving away from each other, like this moves in this direction and this moves in this direction. This is the symmetric stretching mode. There is an anti-symmetric stretching mode, but that does not is not contained in A1, that is contained in B1. I have just done this for the A1 case. So this will be a stretching mode, and the bending mode will be these hydrogen atoms will come to each other, and as the mo- what is that called, center of mass should be conserved, the oxygen should also move up and down as these hydrogens come down and up. So that is compensated by this -2. These go in one direction, these go in the opposite direction. The sum should be 0. This is done with the assumption that oxygen and hydrogen have the same mass. Now, as we have already done this classical mechanical treatment, what this classical treatment can tell us that suppose these normal modes, we have constructed it from a Hamiltonian which looks like this. If we want to treat quantum mechanically, then if this Hamiltonian gets quantized, then also these normal modes will get quantized. This semi-classical knowledge we can use to construct the quantum mechanical structure. So these normal modes will be like energy eigenstates of the system. So this classical treatment is useful. So another thing is, for quantum mechanical treatment, we will have to concentrate on some facts. First is, suppose particles are in vibrations. What this basically mean is that the group elements, they commute with the Hamiltonian of the system. Now, this when I write G, this actually means the representation of the group element on the Hilbert space of the system. This Hamiltonian is also represented on the Hilbert space of the system, so we can consider the commutator, and when that is zero, we will call that the system has the symmetry of this group operation.
Well, when you say capital G comma H0 is 0, you actually mean all the small. So this capital G, either use T small g here if you're going to say for all small g belonging to
Yeah, yeah,
capital G,
this will be small g actually.
D of
D of
small g it
small
is.
g.
Yeah. Otherwise, this is a perfectly standard notation, but for that you don't have to say for all small g belonging to capital G. It actually is meant to mean that. If a capital
Oh.
G comes with H0, what you mean is every element of capital G has a representation which comes with H0. That's a shortcut for way of writing this.
Oh. Actually, I just did a mistake. I wanted to write small g, but by mistake I.
Okay, go ahead.
So, and the second thing is, if suppose we have some irreducible representation of this operator, let's say we have this representation of the Hilbert space, and we are concentrating on a invariant subspace. Then, if we take some element from that invariant subspace and act this operator on that vector, then we will land in that invariant subspace, and that will have the same energy, because if we apply this Hamiltonian on this thing, it will just commute and take out the same eigenvalue as this one. So what we observe is this: if we take any invariant subspace, that will have the same energies, but a invariant subspace can repeat multiple times. So those repeating subspaces can have completely different energies, but in a particular, for example, this is a picture I have taken from a book. This is a typical example of energy eigenlevels. Here they have given the names like A1 is this irreducible representation, is this two degenerate irreducible representation. Irreducible represent two-dimensional irreducible representation. This is a three-dimensional irreducible representation. So all these states have same eigenvalues. Now the same representation can occur again. These two will can have different eigenvalues from these two, but these two will have same eigenvalues as each other. Now, suppose our goal is, suppose we have a molecule in some container, and we shine some light of some particular range of frequencies, and we want to know whether some particular frequency will be observed by the molecule in that container. So for that, what we'll have to study is, suppose an electron is in a particular energy level. Then our question is, if it absorbs some energy, can it go to some higher energy level? So suppose the initial state of the molecule is denoted like this, what is alpha is the representation and I is basis in that representation. So suppose from an initial state we want to see whether it can reach to a final state or not. These are two energy eigenstate. In general, they can have same eigenvalues or different eigenvalues. The thing is, if we want to know the probability amplitude of an electron to go from this state to this state, that will be actually proportional to the external perturbation that we are using to part of the actual Hamiltonian. That will certainly break the symmetry of the system, and that is the reason they can go from one state to another. And this probability amplitude is proportional to this expression. This comes from the I mean first ordered term of Dyson expansion. The first term exactly looks like this. There will be an integral over time, but that is unnecessary. For this analysis, we just need this inner product. And we have, instead of using bracket notation, I have represented in function space representation, because we will ultimately use these no, function space representations to analyze them. So here the function space representation is, I mean, the position configuration space representation is much useful. So now, in many cases, actually, we can save just from the symmetry of the molecule that such transition can take place or not, even without computing this complicated expression for some V. We obviously not need to know the V, but we can skip this computation. So for this, we will look at this general Wigner-Eckert theorem. Uh, and we will use a particular case where this M is identity operator. And as identity operators commutes will all group elements, so we can just write it like this, that if this expectation value will be 0 if they belong to different representation, or even if they belong to the same representation, that I and j, that is they must be the same basis vector to jump from one state to have a transition. Now if this is equal and this is also equal, to have an observation, the energy must be different. So our goal will be, like, for example, we can this jump from this E to this E like this, or DC to some F1 also it can jump, because there is this V factor we can which can change the transformation structure of this whole object. So this whole object is important for our analysis. The uh, final formula that we will use is this, that the, sorry, I think I have made a small mistake actually in writing this. This V will actually not be there. I don't know why I made this mistake. This V will not be there actually. What will be there is this whole structure will represent some representation, whether irreducible or reducible. If there is some irreducible representation here, that is, if V is not there, just psi alpha is there, then this alpha and beta must be equal for some transition. That is, this whole structure will should act like some irreducible representation of the trivial representation. Then only this transition will take place. This V will not be there. It was a mistake. So the kind of transition that we want to look is, if we shine some light, electromagnetic radiation, there can be two terms. An electromagnetic radiation have both electric and magnetic field, and for each of them there will be some potential factors. Now we are treating this electromagnetic field classically, so we can just concentrate on this momentum operator and the angular momentum operator. These are just
Uh,
classical variables, and their transformation properties are unimportant for.
I have a small doubt. The potential for electric field should be E bar Q, right? Like that would be the additional energy. So why are we using velocity here? Momentum.
Say again? Can you please say again?
I mean,
Mm.
how did you get the form E bar dot P bar? The energy cost for any electric field would be
First of all, P, I think that's you should clarify what that P is.
P is momentum.
Really? Are you sure?
Sorry,
It's called electric
it's dipole
dipole
moment.
transition, right?
Why I'm saying momentum? It's a dipole moment, and I
Yeah.
think I have written momentum everywhere. Why I don't know,
Okay,
but
that's exactly the point. I think that's what is confusing people.
this is a
That P is
dipole
a
moment,
dipole
and
moment, and
yeah, I don't
could you
know what.
explain quickly how why is it the dipole moment?
This is dipole moment because the form of the potential energy is for some particle in electric field is it's I think some gradient of electric field dot dipole, something like this, as a form.
No, you are messing up some very basic physics, right? The potential essentially is if it's a uniform electric field, then the electric field, it would have been just electric field into distance with a minus sign, right? That's minus E dot R.
Yeah.
That's for uniform electric field. Now, you might, of course, argue that the electric field due to a light wave, of course, is a wave, so it's not uniform. But when you say electric dipole transition, you're actually making an approximation. Can you tell us what that approximation really is?
Frequency is very small.
Well, yes, what you're really assuming is the wavelength, which is typical for, say, visible light or even ultraviolet light. The wavelength is much, much bigger than the size of the atom. So, within the region where the wave functions have support, that is, they don't vanish, the electric field stays almost uniform. As a result, you
Hmm.
get the dipole approximation, where P, of course, is a dipole moment. It's just Q times R. Of course, if that is there, then there should be no E outside.
Yeah, that's true. Actually, I copied this expression from a place and didn't look at this.
Okay, anyway, go ahead. The basic
The,
idea is
this
this
ex-
is dipole moment, not a
yeah,
which is a vector. So that's that actually the group theoretical argument will not be affected, but you can't identify that as
yeah,
momentum. It's not definitely it's not momentum.
yeah. I have written also momentum, and that has been a complete mistake. This will be the dipole moment.
Okay, fine, go ahead, go ahead. As long as
And,
everybody's clear about that, no problem.
and this dipole transition is this is the formula mu dot b that we use. This magnetic moment is E times S by M. There will be two minus sign, one minus sign for this negative charge, and one minus sign appears in the formula, that minus vector mu dot vector b, in the same approximation. So for electric dipole transition, this is the potential, and the magnetic dipole transition, this is the potential that we'll be seeing. Now, what we want to do is, we'll have to look at expressions of this form. Now I'm talking about this expression with the v, but actually in this statement there will be no v, but for referring what I'm talking about now, I'm considering this v. So we'll have to look at expressions of this form. It's expressions of this expression, and um, we have to see this whole structure v times psi I alpha of r, how they transform under the group operations. So it will transform as a tensor product of this v and this psi alpha, because they are represented in the function spaces, their components are multiplied, so this is component of a tensor product representation. So for that, we'll have to consider the tensor product representations of this group that we are considering. So the I have constructed all possible tensor product representations where the right hand side have only A1 and B1. A2 and B2 we have not considered, because we have already saw classically that there are no modes which correspond to A2 and B2. This semi-classical there was the semi-classical argument that there will be no modes for these two. So this tensor product will actually, as each of them are one-dimensional representation, their tensor will also be some one-dimensional representation, and then we will think of this thing as some object which transform under these one-dimensional representations. Then what happens is, if this object, the irreducible representation under which this transform, it is if it matches with the irreducible representation under which this transform, then a transition can take place. And we will see that actually no transition is forbidden. For example, from A1, something can electron can jump from B1, also from B1 to A1. By the way, the most important point was here, I forgot to mention that I have considered A1, A2, B1, B2. But if we are considering electric dipole transition, then this dipole moment, this is a polar vector. By polar vector, what we mean is something which transform as the x, y, z, these basis functions. So the the polar vector will also be appearing in these rows A1, B1, and B2. So when we will consider only the electric dipole transition, we should be looking at only A1, B1, and B2. And only from A1, B1, and B2, these two are A1, the B1, and B2, we can see that there will be, for example, from A1, if we go to, we want to go to B2, we will see that we can actually go to B2 from this representation. So your final state uh, be a B2 representation, then we will have a transition. So no transitions are actually forbidden for IR spectrum for water. So we are considering a different example where we will actually see such forbidden transition. For example, this is the ammonia molecule, and the symmetry group of the ammonia molecule is C3V. C3 is basically rotation by 120 degree about the principal axis, which goes through ammonia, sorry, which goes through nitrogen, and between from the middle of the three hydrogen atoms. And there are three sigma V planes which go through nitrogen and each of the hydrogen atoms. uh, three sigma V planes and two C2 because C3, because one is 120 degree and another is 240 degree rotation. And then there is the identity. So we have this representation. This is the irreducible representation part. E is used to denote two-dimensional representation. And then we have these, here we have tensor product basis to represent this two-dimensional representation. Now, for the same reason, we are considering tensor product representation of these irreducible representations. Um, Here, we have assumed that somehow we know the energy levels of ammonia, and we know that there is some energy level which correspond to A1, some energy level which correspond to A2, and some energy level which will correspond to E. We have skipped the classical calculation or so the important thing is here, if we look at, for example, a transition from A1 to A2, we will see that we can't find any transition from A1 to A2, both for electric dipole moment and magnetic dipole moment. The reason behind this is if we want to go from A1, then we will always uh, reach either A1 or E, but we can't reach A2 in any way. Similarly, from A2 we can't reach A1. These are symmetric relations. We can't reach A1 from A2. No, we can reach A2 from A2, or we can reach E from A2, but we can't reach A2 from A1 from A2. So this is the reason this A1 A2 transition is forbidden in ammonia molecule. So we have seen that the group theoretic argument has can conclude us that no transition will take place between these. Now, for the cases where a transition take place, the accidentally the amplitude may be very small that it may not be observable. We can say anything about that, but when we say forbidden, we are definitely sure that this transition won't take place. So this is a usefulness of this group theoretic perspective. So I've used these mainly these two references for my uh, thing. The classical part was actually taken from this book by Landau and Lifshitz, and the quantum mechanical part is taken from this book. For example, the picture that I shown the energy level, typical energy level, that is taken from this book.
Okay, so you're
Mm.
done, right?
Yes.
Anyway, good. I think we should all applaud him. This is it's pretty good. But
Thank you.
now, the bad part. Any questions from the audience? None? Or is there a sort of pact that nobody will ask questions?
No, sir, nothing like that.
Okay. So let me just ask one question. This you can reach this particular irrep from this. I'm not sure I understood that. Exactly what do you mean by that?
Sir, can you please explain again?
No,
I
when you
didn't
say
get
that
it.
there will be transition, for example, you said that certain transitions will not occur in ammonia. Okay, could you
Yes.
just explain that once again? Say there's A1 to A2 transition. Why is it forbidden according to whatever table you have written down?
The reason is what we have done is we have to look at this expression, and what
Hmm.
I'm saying is this V times psi alpha, this whole object should transform some under some irreducible representation, which should match with the irreducible representation under which this transform. Only
Well,
then this expression
that's
can be non-zero.
almost correct, except that what you're saying is specifically correct for 1D irreps. But if you have multiple dimensions, then it's slightly more complicated than that. What
Yes,
you're
this
really saying is something like this, that this integral, after all, is an integral which should be invariant under all the group operations, right?
yes,
And that means that it should be able to transform like the identity representation.
yes,
And that is basically the reason why, behind what you're really saying right now. That is, if you were to apply a transformation, each one of the factors, the psi is transformed like some under some irrep. In
mm,
this case, for the water molecule, they were all 1D irreps, so they essentially transformed like the irreps themselves, or multiple copies would transform like an irrep. Multiple
mm,
wave functions, that is, if you have multiple dimensions. That's a more interesting case. We would also, in this case, as you said, V is a dipole, so it's basically like behaves like a vector. So it transforms like one of those irreps. You wrote down what x, y, z components. Those are not only for translations; those are for any vector.
yes,
So they transform like, and that's why it's basically the direct. One way you could put this is the direct product of all three should have the identity in it. But it's
yes,
sometimes easier to just think of direct
mm,
product of two would have the other one in it that will actually also be equivalent that you can show.
yes,
But if there is no identity part, that would mean that this particular integral will definitely change when you did the when you did all the group operations, which of course it can't.
yes.
So the only
Only
way it
way
can
it will
change and
be
yet
zero.
not change is P0. Okay, I think this is
No, I
great.
actually
Anyway,
think
any
I forgot to mention a small thing that the when we talk about magnetic dipole transition, this angular momentum vector, this is actually a axial vector. So they transform like these
the R's right in your
are
table?
thing. Yeah. So we have to look for those cases
Yeah,
only.
A to N E in that case.
Yeah.
You can even talk about specific polarizations because you see, Z, for example, belongs to a different irrep than X and Y, or RZ belongs to a different irrep than RX and RY, or right? Or
Yes.
you have written RZ twice. I think that's a mistake. So you should
Yeah, it will be RX and RY.
yeah. Anyway, this was pretty good. Thank you.
Thank you.
So, who is next? Does everybody need a tea break?
Yes, sir. 5 minutes would be
So we
helpful.
can have a tea
And
break
it's
and
my
come back at
turn next, sir.
yeah. Okay, so since the speaker is going off for tea, we'll wait. We can come back at 5.